noise in single balanced mixer. We are starting with a single balanced. To understand the methodology we need to apply to analyze the noise, and same methodology can be also applied for double balanced. Let me draw the circuit for single balanced active mixer. Here we have got 3 transistors and 2 resistors. Let us start with this M1. So if we have to add the noise source of M1, you can just put a current source in parallel to M1, and this noise source due to M1 is going to flow either to M2 or through M3 depending on what is the VLO value. So in a way we can say that this noise IN1 is going to be multiplied by a square wave. If we are just looking at, let's say, the VIF1 output, and once we understand what is the noise PhD at this output, we can easily extend the same argument to find the noise PhD on the other output. Let me call it VIF1, VIF2, and the current here also I can call it as IIF1. This is IIF2. Let me first try to understand what is the transfer function from the IN1 to this IIF1. So first we are looking at noise due to M1. We can find IIF1 as the current from the M1 being multiplied by a square wave, because if you remember, we assumed that there is going to be abrupt switching for M2 and M3, and because of this abrupt switching, you can just assume there is a square wave with the period of a TLO decided by the LO period, and as a result of which this current at the IF1 you can see as some square wave getting multiplied by this IN1. So as to understand the power spectral density at the IF1 current, we need to understand the frequency spectrum for this periodic square wave and this noise current PhD IN1. So draw so we know for the square wave we are going to get the C term is going to be there. Then we have fundamental component. Then we have a third harmonic. This is then we have fifth harmonic. Frequency spectrum of square. What about the frequency spectrum of noise from the M1? So if we are considering the thermal noise, it is going to be here 450 GM1. So here considering only so we will separately consider the flicker noise due to M1. Okay. So if these are the two spectrums, or the square wave and the noise, after convolution, again we will see that the same kind of spectrum, but the power of this spectrum is going to be scaled by what is the power of this square wave. And here we can see that since it is going to be a 50% duty cycle, so this is going to be, let's say, 0.5. In such a scenario, if we find the PSD of the current in the IF1, that is going to be reduced by half as compared to the thermal noise coming from the M1. So this is a very important intuition, and you can also easily derive by doing the actual convolution of mathematically for the square wave and the white noise. Here I will directly write that the noise PSD due to the thermal noise in the IF1 is going to be equal to half of KT. Let's actually see that depending on what is the duty cycle of this square wave, accordingly the noise PSD is also going to scale. Duty cycle of switching signal as Q of T. Okay, so this is important, this factor of half. Now, if we are interested in the total noise at the output voltage, we can easily see. So similarly, the half of the 4kT gamma GM will be appearing at the IF2 also. And when you take the difference, you are going to get this to the twice of the noise signal power. So the noise at IF due to M1 thermal. It's only a thermal contribution. This noise PSD is going to be twice of the current noise PSD, which we are getting at one of the branches. So it's going to be 2 into half of 4 kT gamma GM 1 into RD square. And if you look at the output, you also have the noise due to this RD. So we can add this noise anyway on top of it separately. So we get this as 4 kT gamma GM1 RD square. Now let us look at the flicker noise contribution from the M1. So the flicker noise is mainly the low frequency noise, and this low frequency noise, you will see that once it appears at this IF1 and IF2 switching by the LO signal, this low frequency noise will appear as some kind of a common mode at each of these outputs. So when we take a difference, this flicker noise will get completely cancelled and there won't be any effect of flicker noise from the M1 to the output. So IF to M1 flicker is 0 as flicker noise, which is low frequency, appears as a common mode at the 2 IF ports. Okay, so the thermal noise appears whereas the flicker M1 is cancelled. I hope this conclusion is clear to all of you. And normally, if you remember, when we try to find the effect of the noise source to the output, we used to find the transfer function. And if you see the transfer function from here to this IF1, for example, is going to have this 2 1 by pi kind of a term coming into picture. But right now, this thermal noise is not a narrow band noise, just like our signal. Our signal used to be narrow band like this, whereas this thermal noise is everywhere. So as a result of which, the thermal noise from all the harmonics will be contributing to the components at the baseband. And in such a scenario, when we try to find the thermal noise at the output, it is not just scaled by this 1 by pi, and we see that it is just getting multiplied by the duty cycle of this switching signal. Now let us try to understand how noise due to M2 and M3 appears at the output. So when analyzing noise due to M2 and M3, we have to keep in mind that they are undergoing large signal switching. So we cannot just assume that noise coming out of M2 and M3 to have a stationary behavior. Meaning the statistics of the noise from the M2 and M3 are also going to change with time as they are undergoing large signal switching. And another point is this switching is also periodic. So their statistics are also going to see this periodic change. In such a scenario, we treat the noise due to M2 and M3 as a cyclostationary random process. Whereas the case of M1, we have treated the noise as a stationary random process. So M2 and M3 undergo large signal switching So it means is due to M2, M3 is not stationary random process. Meaning is the statics are going to change with time. For example, if you have to observe the noise due to, let's say, M2, let's say we have access to the noise in the M2 drain current, we'll see that it is going to be present for some time, then absent, again present, absent, and so on. And this periodicity is going to be decided by the LO signal. Is LO. This kind of periodic behavior, when observed in a random process, this is also called as cyclostationary random process. Cyclostationary due to periodic nature of noise statistics. So this makes the understanding of the noise more involved, because now we need to be careful of what is the region of operation of the M2 and M3 when we are trying to understand its noise contribution. To simplify the analysis, we will split the region of operation for this into three parts. The VLO is sinusoid like this. And if I have to draw the current IF1, where IF1 is this current, okay, which is flowing in the drain of M2. And this IF1 is going to be, so when VLO goes high, we are assuming that entire current of M1 is steered towards IF1. Let me also assume that under this condition, we are not worried about the VRF signal being applied. So here we can just fix this current as some bias current. Right. Bias current in the M1. So this I0 is going to be completely steered towards the M2 whenever VLO goes high. So see that this will go to I0. It is going to be 0. Similarly, if I had to plot for the IF2, it would have been a complementary signal. And this is happening at a period TL. So during this period, we can just say that the MOSFET is in saturation. This is saturation. Period cutoff And during this region, there is a small transition duration. So this, and here in this transition duration, the MOSFET is switching between saturation and cutoff. Me highlight this transition region. So during this saturation, if you look at the equivalent circuit is going to be where only M2 is connected, where M3 is turned off. So during saturation, the equivalent circuit can be, here I will show this I0 current. Here we did not show the M3. So during this period, this is the equivalent circuit. And if at all there is any noise in the M2, this noise is going to just loop back in M2 itself. Because here we have a very high impedance looking downside. So this M2 will see very strong degeneration. So any noise current will just loop back and nothing will appear at the output. So IF1 will be having zero contribution due to M2 when M2 is completely turned on while M3 is turned off. Due to M2 present here at IF1. And anyway, when M2 is in cutoff, again it is not going to add any noise. So only other region we are left with is this transition region, and during this transition region we can try to analyze the effect of noise in a slightly different way. Now looking at this transition duration, we can just talk about this M2 and M3. And we can see that this switching completely depends on the gate voltage which is applied. Now, if we refer the noise of M2 to its gate side, then we can model it as a noise which is coming in series with the VLO signal. Okay. So if you look at the gate voltage of M2, it is not going to be same as this VLO. It is going to be VLO plus some VN2. So as a result of which this VG2 will be having slightly different waveform. More or less it will look like VLO, but when VLO becomes very weak, close to the zero crossing, the effect of VN2 can be visible. Okay. So what will happen is the instant at which this transition happen may also get affected, because the switching instant depends on when this VG2 minus VG3 actually sees this transition. Okay, so it's not just the plus minus VLO, it's effectively what is the VG2 minus VG3, and this VG2 minus VG3 is going to depend on VLO as well as the input referred noise. Let me call this node as VG3, and in this simple circuit, if I have to plot VG2 minus VG3, this difference voltage will decide when the switching takes place. And we know that it is going to depend on this VLO. So the difference is going to have an amplitude of 2 VLO max. Okay. And when we add this noise VN2 top of this, so we know this VN2 is going to here, then it is going to be 0. So this is your VN2. So the net result is going to be, we will be getting this VG2 minus VG3 equal to 2 VLO plus VN2. Okay, so this is what we are going to plot. More or less, it is going to follow same VLO, but near the zero crossing, there is going to be some effect. So this is your VG2 minus VG3. See that there is a region here is not certain when the zero crossing actually takes place. Movement here in the zero crossing will depend on what is the value of VN2 at this moment. So switching time instant depends on VN2, okay, as well as this delta T will also depend on what is the slope. Okay, so if the slope is known and you know what is the extra VN2 which is present at this moment, then accordingly this zero crossing will be shifted by a value Vn2 divided by the slope, and slope of VLO. Is, so let me call this as some delta T. Okay, this delta T to be equal to Vn2 divided by slope of L, where delta T is shift in switching instant compared to the ideal switching instant, let's say, which was at TLO by 2. Now it is going to be TLO by 2 plus some delta T. Okay. So what is the impact of shift in the switching instant? switching instant will shift. So accordingly, this I naught, which was nicely alternating in a symmetrical way between M2 and M3, will also see some perturbation here. So sometimes the I naught will switch early, sometimes the I naught will be switching a little bit late. So this error which is going to appear in the output will give rise to the noise at the output, and this shift is, we can see, directly dependent on what is the noise added by the M2. So the impact is that if I have to take the difference of I2 and I3, okay, because the difference of I2, I3 is going to give rise to this differential output. So this is how the current in one of the branch looks like. If I take the difference, then the difference is going to have these errors. I'm taking the difference. In the difference going from I naught to minus I naught. Okay. And the impact is there can be extra narrow pulse which may be present near the transition. So these are the so this is your TLO by 2. TLO. Here is the T. So these narrow pulses are going to give rise to noise at the output. So if I just take this narrow pulses out, I can draw them as this kind of bars. So whether this shift is going to be positive or negative, accordingly, this extra error which we are getting is going to be either plus 2I naught or minus 2I naught. So we can draw this error pulses as, for example, in this case, this transition happened before the desired instant. So it means we can say there is a negative pulse of minus 2I naught being added to the correct output. Okay. Similarly, here also this is delayed. So you can say there is a minus 2I naught pulse of some duration delta t added at this instant. And here This transition is happening a little early. We can say there is a pulse of plus 2 I naught added at this instant. This is around 2 LO by 2. This is around TLO. We understand the effect of this I error. We can actually find what is the effect of noise on the output. So one approximation we can do here is, since this delta T1, delta T2, delta T3 are going to depend on this value of Vn2 here, Vn2 here, Vn2 here. Just approximate it with an impulse whose strength is equal to the area of these pulses. So this is going to simplify the analysis. Approximating error pulses with impulses of strength equal to pulse area. Now this is important because it will help in simplifying the analysis. So I can write this I error as the train of impulses which are scaled by this 2I naught into delta t train of impulses is appearing at every t LO by 2. Which I can rewrite as 2I naught Vn1 t, because this delta t at any time instant depends on what is the noise voltage and the slope of the LO signal, divided by SLO t minus TLO by 2. So we are interested in the noise due to these error pulses, the baseband frequency, the IF frequency. We can find the noise in the frequency domain as In due to M2 to be equal to 2I naught by SLO. In the frequency domain, it will be a convolution of the frequency spectrum of each of these two. Here it will be again a train of impulses and appearing at twice of the LO frequency scaled by 2 by the LO. With this summation. Okay. Now we are interested in the effect of noise appearing close to the IF frequency. So this Vn1 will have 2 components, flicker noise and thermal noise. The flicker noise is mainly concentrated at the low frequency. So it will be just scaled by this impulse train at DC and appear as it is at the output. Whereas the thermal noise, which is a broadband noise, when it is going to be convolved with an impulse train, its PSD will not change. So again, that noise will also appear as it is at the output. Okay, so please correct. This is VN2, VN2 here. This is so the noise PSD in the IF1 due to M2 going to be equal to the noise PSD of M2 scaled by 2I0 by SLO into 2 by TLO square. Okay. So rewrite this as 2I0 by SLO, assuming VLO is a sinusoid waveform. So we know SLO we are talking about was the slope of this 2 VLO signal, because we are interested in the difference between VG2 and VG3. So this is going to be equal to 2 VLO max into the omega LO. That's the slope. Okay. And by TLO is same as 2FLO whole square simplification. So here also this omega LO will be 2 pi FLO. So it will just become pi. Rewrite this as I0 by VLO max whole square multiplying with the noise PSD of M2. And this includes both, okay, including flicker and thermal. So now we have got the noise PSD of due to the M2. M3 also identical analysis. So if I have to write the noise PSD of IF due to M2 and M3, it is going to be equal to twice of this into 1 by pi I0 by VLO max whole square into VN2 square. Okay, because this VN2 noise PSD is same as VN and the noise PSD of M3. This is the current noise PSD. It will also multiply with RD square. And now it is voltage noise PSD. So here we'll notice that there is a VLO max coming in the denominator saying higher will be the swing of the LO, higher will be the slope, faster will be the transition. But also there is a limit how high can be this slope because or how high can be this amplitude because of the way we are biasing the transistor. And another thing is this I0 is coming in the numerator. So higher will be the bias current, more is going to be the noise due to the mixer. So one way to reduce the noise at the output is by trying to control what is the bias current in the mixer. Okay, so noise due to RD is very simple. We can easily see that the noise due to each of these will come as it is at the output. So we can write the total noise VNIF as sum of all the noises. So here we have noise due to M1, which is only thermal, 4 kT gamma, GM1 RD square, gamma GM1 RD square, plus we have got this 2 by pi square, I naught square by VLO max square into RD square. And here we are talking about the input referred or gate referred noise of M2 or M3. So it is going to be 4 kT gamma GM2, 4 kT gamma by GM2 plus the flicker noise is going to be KF divided by WL Cox either 2 or 3. Okay. So this is a contribution from the M2 and M3. And finally, due to the resistor, we are going to get 4 kT RD, and it is going to be twice of it because we are taking the differential output. So both the RD are going to contribute. So now I hope all of you have got an idea about how to go about analyzing noise in a circuit like this mixer, where the transistors are undergoing large signal changes. The large signal change make the noise analysis also more involved, where we need to figure out how is the noise contribution from different transistors are happening and at a different duration.